Hey there, this is Chris Clements again, here to talk to you about atomic structure. We'll go through the history stuff. This will be a pretty short one as my guess. Okay, let's start with very old theories. Was put out mostly by Democritus. You don't have to worry about dates or anything about that, but Democritus was the first person to propose that matter was not indivisible, meaning folks did not think matter could be broken up, and then they thought, okay, well, it can be broken up, and it can just be broken up and broken up and broken up. Well, he decided that no, there is a limit to that, and we can get to the smallest particle. He referred to that smallest particle as atomos, which of course links us to our current word for that smallest part of matter that is representative of a pure substance as being an atom. So he also proposed that matter is simply empty space through which those atoms or atomos would move. Pretty much on target, actually, but his ideas were not widely accepted because a more, well-respected gentleman whom you've heard of named Aristotle disagreed with that empty space idea. He really didn't think Democritus was on target at all and made that clear, and believed that matter was simply fire, earth, air, and water, and nothing else, and refused to acknowledge Democritus's ideas. Well, gee, do we know who to believe now? Then way ahead in the future, a gentleman named John Dalton proposed what's known as Dalton's atomic theory. In Dalton's atomic theory, there are essentially parts of it that are still true, parts of it that needed to be amended somewhat. So the parts that are still true, I'll start with the first one, is that all matter is made of atoms. That is still true. We still accept that. The second tenet of this theory is that all atoms of a given element are identical and are different from atoms of other elements. Well, this part had to be amended because you might recall that atoms of a given element are not identical because isotopes exist. Now, this is going on the assumption that you know something about atoms, and you know that they're made of protons, neutrons, and electrons. And we'll get to that discovery of those subatomic particles in just a bit. But knowing that isotopes exist, you might recall that isotopes differ from each other. Say a carbon-12 atom differs from a carbon-13 atom because it has a different number of neutrons. That's the only difference. They have the same number of protons, the same number of electrons, they just have a different number of neutrons, which means they have a different mass. So that part of Dalton's atomic theory did have to be amended, but it's still true for what he knew at that time. The next part of it says atoms cannot be created, destroyed, or divided into smaller particles. We know that that's not exactly true these days either, because we certainly can divide them into smaller particles. We can create them per se, not really from nothingness, and we can destroy them per se, not truly destroy them again into nothingness. But we have to use nuclear means to do so, and he just, of course, was not familiar with nuclear means in the probably 18th century when he came up with this. And let's see, the next one is that atoms combine in simple whole number ratios to make compounds. It means that you don't have 1.5 of a particular atom, for example. You're not going to have a portion of an atom. So they combine in whole number ratios to make compounds. What that translates into is we're never going to see a subscript that is not a whole number. So that when you have H2O, it's not the same thing to write it as H. What would the ratio be? If it's 2 to 1, it would be O.5. We won't see that ever. And let's see, the last part is that in a chemical reaction, atoms are separated, combined, or rearranged. And both of those last two tenets are still correct, as well as the first one. It's the second and third ones that needed to be amended a little bit. Next we go to a gentleman named J.J. Thomson. He did a lot of work with what are known as cathode ray tubes, or called CRTs. TVs used to be called tubes because they had CRTs in the back of them. You don't encounter too many new televisions with CRTs in them, by the way. And all a cathode ray tube is a piece of glass with gas in it that has a cathode ray traveling through it. Well, what he deduced was that the negatively charged particles that flowed through the cathode ray tube were actually electrons, what we know now as electrons. So he is credited with discovering the first subatomic particle and naming it an electron. He proposed a model of an atom to try to explain what he knew about an atom. For example, he knew that an atom was neutral, that it didn't have a charge. So he proposed what's known as the plum pudding model. And in the plum pudding model, he thought that an atom was this positive mass that had little negative bits just scattered throughout it. That it was a diffuse positive mass, a spread out positive mass with negative bits in it. And it's known as a plum pudding model because apparently plum pudding is something like a bread with plums embedded in it. I'm not real familiar with that particular article of food and really don't care to be familiar with it, to be honest. All right, next gentleman is Ernest Rutherford. Rutherford actually accidentally disproved the plum pudding model. He and his graduate students were trying to prove the plum pudding model by firing what are called alpha particles, which are positively charged particles. They're really helium nuclei at a very thin sheet of gold foil, assuming if the plum pudding model were true that these very positively charged particles, very densely positively charged particles, would just blast through the gold foil because they wouldn't be repelled by anything. But what he noticed was that some alpha particles were deflected at very, very big angles, which indicated to him that they had encountered something positively charged. So he came up with his model of the atom that had a very tiny, dense central portion. Well, what do you think we call that dense central portion of the atom? You hopefully guessed it right. It is the nucleus. He is responsible for naming the nucleus and deducing that it has a positive charge. He thought that the electrons moved through the empty space that surrounded the nucleus, and later decided that the substances that were positively charged in the nucleus were protons. So he's responsible for discovering the nucleus and naming protons and putting us into the model that has electrons moving through empty space around the nucleus, which hopefully you know is getting a little closer to what we accept today. Now, this discovery that I'm about to tell you about happened much, much later than anything else I'm telling you about. In the late 20s, I believe, is when he did this. James Chadwick is responsible for discovering the nucleus, and what he did was reasoned that there was no way the mass of the atom could be what we knew it to be if there weren't another particle in the atom. So he knew that the particle didn't contribute any charge, but he knew it had to have mass. Therefore, he termed the particle the neutron. It has a mass very similar to that of a proton, but no charge. Okay, let's see. Next, we're going to Niels Bohr. You might have heard of the Bohr model. It's usually the one that most science teachers stick with. And it is a good model. It just doesn't work for every atom. He proposed what's known as the quantum model of the atom, where the electrons don't just float around in the empty space, as Rutherford thought. They actually follow distinct orbits around the nucleus. So his models usually coined cutely as the solar system model because it resembles what we think our solar system looks like. It works for hydrogen, and it works beautifully for hydrogen. It just doesn't tend to work well for any other atom. So it's not very useful, mind you. No, it really is a very useful idea, and it gets your head kind of around what's going on in an atom. And it's typically what you see as kind of the little model of an atom. Anytime you see a model of an atom, it's typically what's shown. So that brings us to what we currently believe, and that was proposed by Louis de Broglie, a French gentleman, who said that it just didn't make any sense that the electrons traveled in these circular orbits that Bohr had proposed. He proposed that they traveled in more wave-like orbits. And his method actually of his model, rather, not his method, is known as the quantum mechanical model, and it's really the model that we still accept today. He proposed it in 1924. And rather than having just circular orbits again, it almost looks like a ribbon that's being twisted that they end up following. They're known as orbits or orbitals, or what they live in. We will get into much more of this with the next investigation, where we look at isotopes and quantum numbers, electron configurations, and what am I trying to say? Orbital diagrams. So it will be an interesting week in my chemistry class. But really, that's about it for now. I told you it was going to be a short one. That'll get me through one lesson, and I don't think I've ever recorded a podcast this short. We didn't have any kitties meowing or anything. Pretty nice, huh? Thanks for listening. Bye.